Section 14. 13 billion years of expansion. Radiation ceased to dominate the expansion of the universe 50,000 years after the Big Bang and was less than 5% of the total energy density by 8 million years after the Big Bang. And the curvature term is effectively zero. This equation can be solved analytically when only the matter and dark energy terms are significant and the dark energy density is constant, W equals -1. The resulting equation for the scale factor versus time is messier than we want to discuss, but I will give you the graph of the scale factor next. If you want to see more of the math, I cover this in supplemental video number 8. The horizontal axis is time minus now in billions of years. The Big Bang is at the left, 13.78 billion years ago. The vertical black line is now. On the right, the graph goes to 4 billion years in our future. Later sections show other graphs that go further into the future, and the scale factor looks exponential with time. The vertical axis is the scale factor. 0 at the bottom, 1.4 at the top. The blue curve is the scale factor, starting at 0 at the Big Bang on the bottom left. The scale factor now is 1. The scale factor in 4 billion years on the top right will be 1.3. Distant galaxies will be 30% further from us then than now. For the last 10 billion years, from here to here, the slope of the scale factor curve has been nearly constant, with the scale factor increasing by about 0.063 every billion years. The scale factor doubled in the last 8 billion years. In the future, it will double every 12 billion years. The scale factor has increased by a factor of 10 in the last 13.2 billion years, so starting here till now, but will take another 39 billion years to increase by the next factor of 10. The rate of expansion in the early universe was high, here, notwithstanding that it was decelerating. Here is a table of scale factors differing by a factor of 10, and the times associated with those scale factors. The scale factor now is 1, so astronomers' cosmological redshift z is 0 for light emitted now and detected now. Let's look at the left of the blue curve. At best, the Hubble Space Telescope can see galaxies as far in the past as z equals 10, here. Scale factor of 0.09, about 470 million years after the Big Bang. But the first stars are believed to have begun to shine sometime around 300 million years after the Big Bang, and their redshift z would be around 14, here. The James Webb Space Telescope is expected to see the light from the earliest galaxies, even to 50 million years after the Big Bang. Scale factor 0.1111, redshift z equals 8, 0.64 billion years after the Big Bang, is the time at which radiation energy density and dark energy density are each 0.3% of matter energy density, so maximum domination by matter, here where I have my cursor. The cosmic microwave background CMB radiation temperature now is 2.7255 Kelvin, and this scales as 1 over scale factor. At any point on the blue scale factor curve, the Hubble time is the scale factor divided by the slope of the curve. The Hubble time today is 14.4 billion years, a little more than 13.78 billion year age of the universe. In the past, the Hubble time has been more than the age of the universe, but beginning around 1.2 billion years from now, the Hubble time will be less than the age of the universe, as the blue curve bends upward. Matter density decreases as 1 over the cube of the scale factor. Around 6.5 billion years ago, the total matter density of the universe fell below the present value of the matter density of our local group of galaxies. The red line shows the time at which the energy density of matter fell to twice the dark energy density. Prior to this time, the scale factor was increasing but decelerating. The graph curves downward. It's curving downward. After this time, the graph curves upward, and the scale factor is increasing and accelerating. It is curving upward. This is the accelerating expansion of the universe due to dark energy. The inflection point occurred 6.1 billion years ago, at which time the scale factor was 0.61, redshift was 0.64, temperature was 4.5 Kelvin, and the Hubble time was 10 billion years versus 7.6 billion years for the age of the universe at that time. The vertical green line shows the time at which the energy density of matter fell to equal the dark energy density. This transition point occurred 3.6 billion years ago, at which time the scale factor was 0.77, redshift Z was 0.3, temperature was 3.6 Kelvin, and the Hubble time was 12.3 billion years versus the 10.2 billion years for the age of the universe at that time. Now look at the red dotted line. This is the tangent line at the inflection point. Notice that the actual scale factor graph doesn't differ much from this tangent over a 10 billion year period, from here to here. But now the scale factor is becoming exponential with time in the future. Here is a reference table of scale factors and ages for certain redshifts. And here is the continuation. Visualizations of the history of the universe. Here is a beautiful and useful visualization of the history of the universe. Time increases left to right. At specific times, a circular hoop is drawn. The radius of the hoop is a loose representation of the scale factor at the time, so of the expansion of the universe. This helps us to see different epochs and how the distance between distant galaxies has increased over time. But it is not a timeline of individual galaxies. Here is another beautiful visualization showing cosmic microwave background last scattering, dark ages, and the first stars. Here is another visualization that shows the filaments of clusters of galaxies filaments, and the huge cosmic voids between the filaments. Void here, void there. No visualization is perfect or complete, but each is helpful.